Hey everyone, in this video we're going to talk about more methods used to factor polynomials. The polynomials that we'll mostly be concerning ourselves with in this video are those that are called quadratic or second degree polynomials. These are of the form ax squared plus bx plus c. But we're first going to focus on the case when a quadratic is described as monic. The word monic simply just means that the leading coefficient of a is equal to 1. So a more reduced form of what we'll look at first is a quadratic or a second degree polynomial of the form x squared plus bx plus c. The general strategy is the following. I want to look for numbers s and t such that s times t is equal to c, the constant term, and s plus t is equal to b, that middle coefficient. And if such values exist, then I can factor x squared plus bx plus c as x plus s times x plus t, knowing that the numbers s and t could be negative. Please note that this slide is merely offering a formulaic approach because the process itself isn't as bad as it might seem. We'll start off with the following example. Take the polynomial x squared plus 2x plus 1. Here, my b term is equal to 2 and my c term is equal to 1. Remember, I require values s and t that multiply to 1 and sum to 2 in this case. Through a little bit of trial and error, if I set s and t both equal to 1, these values work because s times t, or rather 1 times 1 equals to 1, and 1 plus 1 is equal to 2. Thankfully, I don't have too many things to look through because the number c, which is 1 in this case, only factors as 1 times 1 or negative 1 times negative 1. All I have to do is go through each factorization, add the factors, and see which one of them give me 2 as an answer. But now that I've got that, I can rewrite x squared plus 2x plus 1 as x plus 1 times x plus 1. In this case, since both factors are the same, I can simplify it as x plus 1 squared. What's the easiest way to check that I factored correctly? Well, I can FOIL my factorization and see if I land at the problem I started with. So in essence, this is the process. You take your constant term, see which factors it has, and see if any of those factors sum to that middle term, b, or in our case, a 2. Let's look at another example. Consider the polynomial x squared minus 4x minus 5. Here, b is equal to negative 4 and c is equal to negative 5. The question is, are there any factors of negative 5 that add to negative 4? Through a little bit of trial and error, I'll figure out that if I let s equal to negative 5 and t equal to positive 1, I have something that works, because negative 5 times positive 1 equals negative 5, and negative 5 plus positive 1 equals to negative 4, so everything lines up. Therefore, I get to say that x squared minus 4x minus 5 factors as the quantity x minus 4 times x plus 1, and we're done. Sort of like I was saying before, the values s and t aren't necessary for this process, it's merely just to provide a formulaic approach. Again, all I'm doing is checking to see if any factors of my constant term sum to the middle term, or the middle coefficient, and if they do, then I get a nice factorization rule like displayed in this slide. This next case talks about what happens when my leading coefficient a is no longer equal to 1. In this case, I can't use the same method, but I can expand on it in the same spirit. This is known as the AC method because it involves multiplying my a term by my c term. The strategy goes as follows. First, make a cross. Second, in the north and south positions, input the a times c term and the b term. In other words, I'm taking the coefficient a, the coefficient c, I'm multiplying them together, and I'm putting them in the north position. b by itself goes into the south position. And note that I gotta take any signs that I see, rather any negatives, along with. Next, I gotta find numbers s and t so that s times t equals ac and s plus t is equal to b. So this isn't too dissimilar to what we've already done. But just to keep our bookkeeping, we're gonna place the s and t numbers in the east and west slot. And now once I have found these numbers, I'm gonna make the following replacement to our polynomial, and then we are going to perform the action of factoring by grouping. So I'm going to take ax squared plus bx plus c and change bx into the term s times x plus t times x. This might seem kind of weird, but this replacement of bx with s times x plus t times x will allow us to factor by grouping in a way that always works. For our first example, we'll look at 6x squared plus x minus 2. Here a is equal to 6, b to 1, and c is equal to negative 2. So let's go ahead and fill out our cross. The north slot is going to get a times c, which in our case is minus 12, and the bottom slot is going to get the number 1 because that's our value for b. This process takes a little bit of trial and error. 12 times 1, I don't think those factors will work because no combination of those gives me a 1. Same with 6 times 2. However, positive 4 and negative 3 do work because those multiply to negative 12 and add to positive 1. So basically, after a little guesswork, we can put 4 and negative 3 into our cross, and then we can expand our b term, our polynomial, in the following way. So 6x squared plus x minus 2 becomes 6x squared plus 4x minus 3x minus 2. Then we just simply factor by grouping, and then we're done. So this is really all the AC method calls for. Making this cross on the right helps us with a little bit of bookkeeping, but it's a matter of splitting that b term into two separate terms that allow us to factor by grouping and get a full factorization. For our next example, look at 8y squared minus 2y minus 3. Here, a is equal to 8, b negative 2, c negative 3, so we'll put negative 24 in the north position and negative 2 in the south position. As we run through different factors of minus 24 in our heads, we'll find that the factors of positive 4 and negative 6 are the numbers that we want. They multiply to negative 24, and they sum to negative 2. Then we can expand 8y squared minus 2y minus 3 as 8y squared plus 4y minus 6y minus 3. The last step has us factor by grouping, at which point we get the final answer of 2y plus 1 times 4y minus 3. Anytime you're doing one of these problems and you want to check your answer, again, just FOIL your final result. If you land back where you started, you know you got the right factorization. We'll conclude this video with some special factoring formulas. We've already seen the difference of squares, but we also have a difference of cubes formula, which looks like a cubed minus b cubed, which is equal to a minus b times the quantity a squared plus ab plus b squared. Let's jump right into some examples. Consider x squared minus 4. Notice that I can rewrite this as x squared minus 2 squared. And I'm using parentheses here so I can figure out what my capital A and capital B expressions are, so I can correctly plug them into my difference of squares formula. Doing this, I end up with x minus 2 times x plus 2, and there you go, we have a fully factored polynomial by the use of our difference of squares formula. In the example y squared minus 3, we see that I don't actually have to have a perfect square to make this work. Y squared is a perfect squared, but I can rewrite 3 as the square root of 3 squared. In this case, I'm sort of forcing a squared term to appear out of nowhere by introducing a square root term. This is definitely a legal and useful mathematical move. But now that I've got this written out and I know what my capital A and capital B are, I can factor this as y minus square root of 3 times y plus the square root of 3, and we're done. For this last slide, we'll look at a couple of difference of cubes formula, just because these can be a little bit more involved. So let's look at our term. I have 125x cubed minus 8z to the 6th. I know that 125 is 5 to the 3rd power. I know that 8 is 2 to the 3rd power. I also know that that exponent on z can be written as a 2 times a 3. And now that all of these powers of 3 are visible, I'm going to sort of pull them out so I can write them on top of a quantity that's in parentheses. I do this so I can identify what my capital A and capital B are, so I can use the difference of cube formula more efficiently. So, with the value of a being 5x and b being 2z squared, I can plug this into my difference of cube formula and I'll get the following expression. Even though it's a little bit long, having the identifiable capital A and capital B terms right there in front of us makes it easier to plug them in to the difference of cubes formula. But once I have it expanded, I just simplify and I get a final answer. And for our last example, look at 64 minus x plus y quantity to the 3rd power. Just replace 64 with 4 to the 3rd power, and enjoy the fact that the quantity x plus y is already to the power of 3. So I know that my a term is 4, my b term is the quantity x plus y, and then I just plug them into my difference of cubes formula like I did before. With all this laid out, we'll go ahead and try to simplify as much as we can, and we'll end up with the following answer. And this concludes our topic on factoring and section 1.3. Join us for section 1.4 on rational expressions.